So I'm going to talk to you today about a small subset of the things the sun does, but these are things that are important for us. They actually affect us, in particular in this technological age. They affect our technologies, things that weren't around for our ancestors, but are for us. It's entitled Sunspots, Space Weather and Climate. Let me begin by reminding you how important the sun is, of course. It's the source of light and heat for life here on Earth, and because of this role, it was deified by our ancestors. Its position in the sky was tracked by ancient astronomers, and in particular, noting the turnaround point where the sun stopped its southern trek and started heading northward again, and cause for celebration in December. The sun, of course, is the star at the center of our solar system. It's 100 times as wide as the Earth is, 10 times Jupiter. Its mass is 300,000 times the mass of the Earth. There are 1,000 Jupiters. Surface temperature, a mere 10,000 degrees Fahrenheit. And that temperature rises quickly as you go in until you get to 30 million degrees in the core where the nuclear burning is going on. The density might surprise you. The surface, we would call the surface a vacuum. It's basically the density of air at spacecraft altitudes of about 60 kilometers above the surface of the Earth. But because of the strong gravity of the sun, that gas or plasma gets compressed quite rapidly. By the time you get a third of the way in to the base of the convection zone, the densities increase to about the density of water. Deep in the core, it's 10 times the density of metals like gold or lead, and yet it's still fluid. It still moves around because of the high temperatures. Composition by mass is mostly hydrogen with a fair amount of helium, most of it that it had when it formed, some of which it's making. And then a small percentage of what astronomers refer to as metals, which is anything other than hydrogen or helium. So carbon, oxygen, and nitrogen in particular. Our sun's, we refer to it as a garden variety star, although I'm not sure I really like that word. The diagram here is called a temperature luminosity diagram, or color magnitude, or Hertzsprung-Russell, or HR, a number of names for it. Across the bottom, it's the very hot things are on the left, the cooler things are on the right, the dim things are on the bottom, and the bright things are at the top. Any star in the sky can be placed on this diagram, and what we find is that the vast majority of stars lie along this diagonal strip called the main sequence that goes from the upper left to the bottom right. In the bottom right, you have the smallest stars, a tenth the mass of the sun, a tenth the radius, or they're about the size of Jupiter, actually. At the upper end of that, you have stars that are 60 times as massive as the sun and 10 times the diameter. The other stars on the diagram, the supergiants, the giants, and the white dwarfs, are either dead or dying stars. So most stars spend their time on the main sequence burning hydrogen in their cores. It's after that hydrogen is exhausted that they move to other places on this diagram. So that's a brief introduction to the sun, just to get us all kind of on the same page for this. My talk today is in 3 parts. I'm going to start with sunspots and the sunspot cycle. And since that's my real area of expertise, I'll spend probably too much time there, but I'm the speaker. The next thing is solar activity and space weather. So these are the things that the sun do that influence our technologies, both in space and on the ground. And then I'm going to end up with solar variability and terrestrial climate. The idea that the sun does vary, gets brighter and dimmer. It's actually considerably brighter now than it was when it was born 4.5 billion years ago. And those variations may or may not contribute to terrestrial climate. So let me start with sunspots and the sunspot cycle. Sunspots were discovered within months of the first use of the telescope for observing objects back in 1609. Credit is usually given to Galileo, but the Brits will claim that Thomas Harriot beat him to it. I think it's a virtual tie as to who first reported on seeing sunspots with telescopes. But the real credit goes to the Chinese. The Chinese had been reporting spots on the sun for 2,000 years now. That big spots on the sun are big enough that you can see it without a telescope, but you need smoke like we have in the sky today, or the sun near the horizon to see them. And the thought has always been that the Europeans were determined that the sun was a perfect disk with no blemishes. So if they saw sunspots, there must be something wrong with their eyes. So that was the discovery of sunspots. What they are dark and cooler regions on the surface of the sun. They usually appear in groups that form over the course of hours or even days, and they last typically for days or weeks or sometimes even months. I've shown a picture here of the sun with quite a few sunspot groups on there. Just looking at it, I'd say there's 5 or maybe 6 groups. Underneath, I've extracted a piece of that and shown in comparison the size of the Earth, just to remind you that it's 100 of those Earths side by side across the sun. So a typical sunspot's about the size of the Earth. The earliest observations back in 1610 indicated that the sun rotated in about 27 days. So let's look at the sun up close. This is from the SOHO spacecraft, zooming in on a sunspot, and then I switched to the Hinode spacecraft to look at details of the sunspot on the sun. You might have seen reports in the news recently, the Gregor telescope that the Europeans have on Tenerife gets similar pictures from the ground. In fact, even better detail than this. This is a movie showing the boiling motions across the surface of the sun. They're called granules. Each of these granules is basically a big bubble of hot material coming up out of the sun. They're typically about the size of the state of Texas or Alaska. You see a number of flows in here. You see moving elements in the penumbra, the grayish part of the sunspot moving in towards the center, and then around the outside edge of the penumbra, you see what's called evershed flow, a flow away from the sunspot. So there are a number of flows on the surface of the sun like this that are related to sunspots. Surprisingly, it took over 230 years of observing the sun for astronomers to recognize that there was a sunspot cycle, that the sun produced sunspots and lack of sunspots on about a 10-year basis. Credit for the discovery goes to Heinrich Schwabe, astronomer from Germany. These are actually from his observations. He published his observations. I've plotted them up here as bar charts, and he noticed that over the time he'd been observing the sun, the number of groups, sunspot groups, rose and fell and rose and fell. And then when he looked at the number of days without any sunspots at all, they fit in the gaps in between. Shortly after Schwabe discovered the sunspot cycle, Rudolf Wolf, who was the director of the observatory in Zurich, Switzerland, realized, given this, that there was a need to observe the sun continuously. And he started a network of observers, but this was very autocratic, that he had the final say in what the sunspot number was. But he started this network in 1849, and he also looked back to the previous century to try to fill in what was observed before that. He also recognized the difficulty in actually counting individual sunspots. The number you count is going to depend upon how good your telescope is, what the seeing is like, what the sky is like the day that you observed. So he devised what he called a relative sunspot number, or R. given by the equation in the middle here. It's basically, you count the number of groups. Groups are easier to recognize. And you multiply by 10, as if, you know, a typical group has maybe 10 spots. Then you go in and count the individual number of spots and add that to 10 times the number of groups. And then you put this fudge factor, this correction factor, K, in front of it all. And that fudge factor was designed to kind of normalize everyone's counting so that they would come up with the same numbers. And it was normalized so that you got the same numbers that Rudolf Wolf got. Turns out he didn't have the best telescope or the best eyes. So typically that correction factor was a 0.6. You had to take people with good telescopes and good eyesight, you had to take their observations and multiply by 0.6 before they agreed with Rudolf Wolf. We now have 24 well-observed cycles. The first ones are not so well observed. What I've done in this plot is each little dot is a month and the average number of sunspots observed in that month, and it's color-coded where if every single day observations were made, it's black. If there were, if you're missing 1 to 10 days, it's green. Missing 11 to 20, then it's yellow. And if you're missing more than 20, it's red. And there are some periods, if you look on cycle 4 around 1790, where whole months went by without anyone reporting observations of the sun. But we've got, by Rudolf Wolf's counting system, we're just finished cycle 24 and they're starting cycle 25. Typical cycle lasts about 11 years, but they range from 9 to 14 in length. The average amplitude is about 150. But they range from small ones, half that size, to big ones, almost double that size. Again, we're currently just past the minimum of solar cycle, between solar cycle 24 and 25. Cycle 24 was the smallest in 100 years, and there's actually a modulation in the size of sunspot cycles. So with a period of about 100 years, every 100 years we go through a dip like this. So there were small cycles at the beginning in the early 1900s, the early 1800s. And then there's this period called the Maunder minimum, which is actually a misnomer. Maunder reported on it, but he was reporting on observations by Sporer. So really Sporer discovered it, but it's a 70-year period where basically the sun stopped making sunspots. And it's still a bit of a mystery as to why and how that happened, but will come up as we see later on. Sunspots don't appear just any place. They appear in 2 bands on either side of the equator. This was first noted by Richard Carrington in 1858. This is called a butterfly diagram for obvious reasons. I've put this together from 2 different data sets that I curate on my website. Most of it is from the Royal Greenwich Observatory up to 1976. From 76 on, it's data due to, that's produced by the US Air Force. The colors in the butterfly wings are related to how much of the sun in that latitude strip is covered by sunspots, from just some where it's black to more than 1% of the strip being covered red, or more than 10% being yellow. The thing to note here is that the cycles overlap, often at minimum there are sunspots near the equator. At the same time, there are sunspots at higher latitudes for the next cycle. You also see that big cycles tend to have broader wings and extend to higher latitudes. The key to all of this is magnetism, and this was a discovery of more than 100 years ago by George Ellery Hale. The title of his paper was On the Probable Existence of a Magnetic Field in Sunspots. Turns out magnetism, first of all, magnetism's everywhere. But when you have a magnetic field and you have an electrically conducting fluid, a plasma, the most wondrous things can happen. George Ellery Hale measured and noted that deep in sunspots, there were strong magnetic fields. How did he do that, you might ask? It's through spectral analysis, where you take a sliver of light from the sun, pass it through a prism or reflect it off a grating. You get the full colors of the rainbow, but you'll notice that there are certain colors that are basically missing. They've been absorbed by atoms or ions in the sun's atmosphere, where light at that color is absorbed by the atom and it knocks an electron to a higher level. The little picture at the bottom right, part of that is a picture of the sun, the reddish and yellowish one. And you'll note in the picture of a sunspot, and you'll notice a little tiny slit or sliver down there. Light along that slit is allowed to pass into a spectrograph, and the part of the green part of the spectrum is shown to the right of it. And what you find is that where along that slit there were strong magnetic fields, one spectral line that's sensitive to magnetic fields splits into three, and you can see it there, split into three different pieces, and those different pieces are polarized, so that by using a piece of Polaroid, you can determine not only the strength, but the direction of the magnetic field. Even though we're not right there on the sun, the light from the sun tells us that there's magnetic field there. Magnetic fields are every place on the sun, not just in sunspots, but they loop up out of sunspots to form coronal loops. Again, where the sunspots are, you have the most intense magnetic fields, but every place on the sun, you have the salt and pepper pattern of magnetic fields, white where it's coming out of the sun, black where it's going back in. And wherever those fields are, if you look into the corona, here using ultraviolet light, you see these coronal loops which outline the magnetic field itself above the surface of the sun. So you can visibly see the structure and motion of the magnetic field. A decade later, George Ellery Hale came back again, and after observing magnetic fields on the sun for that decade, noticed that there's something going on. We now refer to this as Hale's law, but what he noticed was that the preceding and following spots in a sunspot group are of opposite polarity, and that the corresponding spots of the groups in the northern and southern hemisphere are opposite. Furthermore, you go to the next cycle and they're opposite again. So with the pictures I've picked out here, and I've put ellipses around the active regions, you can see in cycle 23, May of 2002, in the northern hemisphere, the upper half of the figure, it's white or positive on the right and black or negative on the left. You go to the southern hemisphere, it's flipped around. It's negative on the right and positive on the left. You go 11 years later to the peak of cycle 24, May of 2013, and you now see it's reversed. Now it's the northern hemisphere that has negative polarity on the right and positive polarity on the left, and it's flipped again in the southern hemisphere. Another key part of the sunspot cycle and how it works is the fact that the sunspot groups, when they emerge through the surface, are typically tilted. The leading spots of one polarity are closer to the equator than the following spots. The following spots tend to be at higher latitude and again have the opposite polarity. We can see all of this plus two critical flows in this movie that I've put together. We can peel off maps of the sun every 27 days as the sun rotates. And what I've done is a series of about 4 different databases. I've put these together over 40 years. So you can see the motion of the sunspot towards the equator, and it changing from cycle to cycle, but you also see flows in here. Stuff near the equator is drifting to the right. Stuff at higher latitude is drifting towards the left. That's differential rotation. With the equator fast, the poles slow. You also see a meridional flow. There's a flow away from the equator in both hemispheres, carrying magnetic fields off towards the poles. So all of those are critical in our understanding of the sunspot cycle and how it works. A key part of this is the polar field reversals. In 1958, Harold Babcock, turns out there's a Harold Babcock and a Horace Babcock. Harold's the son, or no, Harold's the father, Horace is the son. But Harold and Bill Livingston noted that the polarities of the sun's weak polar fields, and again, in sunspots, the magnetic fields are 3,000 Gauss. The Gauss is the unit of measure for magnetic field. The polar fields are about a half a Gauss, so they're much, much weaker than the magnetic field in sunspots. And so it took a long time, again, 50 years before the Babcocks had measured the polar fields. But what Babcock and Livingston noticed was that the polar fields reversed at about the time of cycle maximum. And you can see that in this diagram. This diagram is put together from all of the maps in the previous movie I showed that's averaged along longitude in each of those maps. You can see the butterfly wings where sunspots emerge. Key thing in the butterfly wings is you'll notice, because of the tilt of active regions, that the side of the butterfly wing near the equator is one color, one polarity, and the side towards the pole is the opposite. And it's purely due to that tilt of active regions. But you can also see at higher latitudes, magnetic fields being transported away from the sunspot latitudes off towards the poles. And it's the trailing polarity, the high latitude polarity that does that, and it eventually cancels the magnetic field that was at the pole and builds up a new magnetic field. And the time that it flips is about the time of sunspot cycle maximum. So here's Horace, the younger of the Babcocks, came up in 1961 with this idea for how the sunspot cycle works. Most of this is still works today. The devil's in the details, and there's things we know aren't quite right about it. But he considered it in this cartoon, starting in A in the upper left, with the magnetic field at sunspot cycle minimum basically being dipolar, coming out of one pole, looping around, going back in the other, and then connecting in a shallow layer under the surface. We know because the sunspot cycles overlap, it can't be as simple as that, but the basic idea is probably not too far off. Differential rotation takes that field under the surface and wraps it around the sun. So the fast rotation at the equator takes those magnetic fields in and wraps them around the sun, and that wrapping gets strongest at the mid latitudes where the sunspots first pop out. So you go down to figure C, where you see a sunspot, a loop of a magnetic field that comes out in a sunspot where the preceding and following polarities and a slight tilt to it. And then in D, meridional flow then carries primarily the trailing polarity, that in this case in the northern hemisphere, that negative, and takes it off to the poles, where eventually it cancels the old polarity and builds up a new one, and the cycle starts all over again. Again, the devil's in the details, but and still actively researched today, but this in a nutshell is basically how the sunspot cycle and the magnetic cycle work. All right, so now I want to move on to solar activity and space weather. This goes back to Richard Carrington again. We mentioned him before with the sunspot latitudes and differential rotation. He reported observing a large sunspot in the afternoon of September 1st of 1859 and noticed that two patches of intensely bright and white light broke out. And the drawing underneath is his drawing of the sunspot and pointing out the A and B, the two really bright patches of light. Richard Hodgson was observing at the same time, reported the same event, which he described as having the appearance of a very brilliant star of light, much brighter than the sun's surface. So this is what nowadays we call a white light flare. They're rather rare. They don't happen often, but this one was spectacular and had spectacular results at the time. Well, here on Earth, as I'll mention later. Flares are much easier seen if you use special filters. Here I'm going to show you flares as observed in ultraviolet light from two different spacecraft, ESA NASA SOHO spacecraft, the Solar and Heliospheric Observatory, and the TRACE. And SOHO is 1 million miles away from us. It sits at a point between us and the sun and still observes the sun continuously and has been doing so since 1995. So here's a view from that, and you see the flash of the flare. This is from TRACE closer down. You see the flash of the flare, and you'll also notice a lot of noise on the detector, a lot of, and this is actually radiation from the flare hitting the detector we're using to observe it and causing problems. Solar flares release the equivalent of a million megatons of TNT. So this is millions of hydrogen bombs in a matter of minutes. And they always occur in the vicinity of sunspot, but they're incredibly energetic. And remember, sunspot's the size of the Earth, so typically these flares are rival the size of the Earth. Another phenomenon that is related to space weather are prominences. Prominences are clouds of gas that are suspended above the surface of the sun by the sun's magnetic fields. Here I'm using the SDO spacecraft for the full disk, and then the Japanese Hinode mission to look at the details. And this is, again, cloud of materials. It's suspended by magnetic fields, and you see it kind of condensing up there and raining down onto the surface. Lots of prominences are what we call quiescent, and this is a quiescent prominence. It's just sitting there. They're really beautiful to see and to watch. Although you have to do it in time lapse. They evolve rather slowly over the course of a day. But they do erupt into space. This is an eruption seen from the Solar Dynamics Observatory. You see it lift up and a loop of material and some stuff falling back down afterwards. So prominences erupting are another source of what we call space weather. Coronal mass ejections are a big part of space weather. These are often occur in association with flares and prominence eruptions. You can literally have 1 billion tons of matter blasted off of the sun and sent through the solar system at speeds in excess of 1 million miles an hour. This is a month-long movie from LASCO instrument on the SOHO spacecraft. During sunspot cycle maximum, you can typically see several CMEs a day, whereas at this part of the solar cycle, at minimum, you're lucky to see 1 or 2 a week. So they come and go with a sunspot cycle, they come and go with sunspots. So all 3 of these can happen in the same event, and this is a fairly well-known one called the Bastille Day event because it occurred on Bastille Day in the year 2000. Started with a flare. Let's see, and so you'll see the flare go off, bam, and then the detector gets showered with radiation. Here from TRACE, bam, showered with radiation. And then these are post-flare loops that light up afterwards. This is a coronagraph on SOHO where the sun is blotted out so you can see the corona, and you can see the thing blast off and form like a halo around the sun because it's coming straight at us. And you can also see what it did to our detectors. It momentarily blinded our instruments from the radiation that was spewed out by that event. The key to all of this, as with the sunspot cycle, is magnetism. Magnetism is really what makes the sun far, far more fascinating object than if it were just a star that we didn't know had all of these things going on. We've discovered that it's magnetic shear, the twisting of magnetic field in sunspots, that produces flares, and it's that same sort of twisting or shearing of the magnetic field that produces prominence eruptions and coronal mass ejections. So you're basically taking the magnetic field, twisting it up until it can't take it anymore, and it basically short circuits, it reconnects, blasts off with a release of, again, 1 million megatons of TNT. CMEs can impact the Earth and are a source of disturbances to our magnetic field and to our atmosphere. This is a rather crappy image of the sun, this animation, but nonetheless, the animation works where you see a flare, a CME get blasted off of the sun, travels through the solar system, takes anywhere from 2 to 4 days to reach us. We're surrounded by our magnetic field out in space, but that gets ripped apart by these disturbances, wrapped around to the tailward end, and then reconnection in the tail sends radiation, energetic particles into our atmosphere to create the aurora borealis. So for our ancestors, the aurora were about the only indication of space weather or solar activity, but making that connection didn't happen until much, much later. So here's aurora as seen from the ground. These are high latitude aurora. The greens and blues are typically high latitude, and they're look like curtains of light in the atmosphere. These are from particles, energetic particles, electrons and protons streaming into our atmosphere and exciting atoms of oxygen and nitrogen. They don't happen only at high latitudes. This I lucked upon. This is a red aurora, which you typically see at lower latitudes, that was observed in Napa back in 2001. So even as far, in fact, further south than San Francisco and the Bay Area, you can still see aurora, but it takes exceptional events. And unfortunately, at these low latitudes, the particles don't get down low, so they only light up gases high up and they're red. So it's easy to confuse this with a wildfire in the distance. But and again, I saw one of these in 1980 in Boulder, Colorado, which is not a low latitude. The Carrington event in 1859, that flare that Carrington and Hodgson observed, they saw aurora in Puerto Rico, so very low latitudes. All of this produces what we call space weather, and so this refers to conditions on the sun, and most importantly in the environment, the space environment, that can influence performance and reliability of space-based and ground-based systems, but it can also endanger human life or health. So these conditions in space can, the radiation in particular can be harmful to astronauts on EVAs. They need to get inside. It would be harmful to people on flights to the moon or Mars. It's also a problem for aircraft operations going over the poles, that not only do you get increased radiation from these events, but you lose radio communication. So there's problems with polar flights. The radiation harms satellites in orbit. The geomagnetic disturbances can produce surges of power in power lines and take out power. And then the final one, climate change, I'll get to here in just a minute. So the effects on satellites, it's the radiation, the energetic particles that are the main culprits here. And that radiation can take out electronics. And so there's been a number of these. And this slide's about a decade old at this point. And at that time, there were, as I pointed here, 4,500 spacecraft anomalies over the previous 25 years. Some of these are temporary, some are permanent. An interesting one is the Mars Odyssey in 2003. On its way to Mars, it got hit by a radiation storm, big storms called the Halloween events of 2003. The instrument that got hurt was its radiation monitor. Of all instruments, that's the one that took out. Big events like the Carrington event could cause billions, and people have even floated the number of trillions of dollars of damage. So there's a National Academy of Science, National Research Council report in 2008 that claims if the event that Carrington saw in 1859 happened today and was aimed at Earth, it could have the damage of 20 Katrinas. And basically by taking out transformers that we don't have a good stockpile of. Here's an example of that happening in March of '89. An event on March 13th fried, that's a technical word, fried a $10 million transformer in New Jersey, took out power to Montreal, and parts of the province of Quebec were without power for 6 days. So geomagnetic storms like this can be devastating. The reason this happens is that when that CME shakes the Earth's magnetic field, you're a moving magnetic field in a loop of wire, and you make current. And so you produce what are called ground-induced currents that go along power lines and again, fry transformers. Given that there were talk about killer flares, this is again a decade ago, back in 2011 as the next one was coming up. So here's one headline: flares, huge storm will cause devastation. Here we're pondering about the big one being the Carrington event. Here, huge solar flares in the next decade could cause year-long blackouts and a nuclear crisis, says NOAA. Finally, solar flares could cripple Earth's technology and infrastructure in 2013. Well, 2020 is far worse than 2013 ever was. So that didn't happen, but the point is that there's that possibility. Luckily, NOAA, the National Oceanic and Atmospheric Administration, is charged with providing warnings for these. And so they have, like they have for hurricanes on a scale, or tornadoes, on a scale of 1 to 5, radiation storms, and they will give a prediction for how bad it'll be on a scale of 1 to 5. Geomagnetic storms that produce the power outages, and radio blackouts that are caused by X-rays and extreme ultraviolet light in our upper atmosphere. So NOAA has it under, has these warnings that come out and keep a pretty good track of what's going on. And power companies are also well aware of the dangers of this and can take actions to minimize the effects. All right, final bit, solar variability in terrestrial climate. Total solar irradiance, or TSI. Total solar irradiance is a key input to climate models, and it refers to the amount of radiant energy from the sun that crosses a unit area, a square meter, per second at the average distance of the Earth from the sun. And this includes all wavelengths of light, from the infrared far out into the ultraviolet. TSI was previously referred to as the solar constant until it was measured accurately starting in about 1978. So on the bottom here, I show two plots of the same numbers. These are the total solar irradiance as measured on the Solar Maximum mission. There's a little gap you see in the data. That's when SMM had a failure and had to be rescued by astronauts on space shuttle. A good friend of mine, Pinky Nelson, was one of the astronauts on that mission to save SMM. What you see on the left is those numbers plotted on the full scale from 0 to 1500 watts per square meter. And it looks like it's constant. It looks like it's just a flat line going across there at about 1365 watts per square meter. If you zoom in on the top 1% of that plot, you get what we see on the right. And the main thing that was noticed early on was that whenever big sunspots came across the sun during the maximum of cycle 21 back in the early 80s, you'd see a dip as the sunspot went across, which you'd expect. Sunspots are dark. They ought to make the sun look darker. But as the mission continued, and you can see the data gets better after they fixed it. It's not as noisy. You still see the dips from sunspots, but during minimum, the level is lower than it was at maximum. So the sun, and this was a bit of a surprise, that the sun is actually brighter at sunspot maximum than it is at minimum. We now have 3.5 solar cycles of this. And so the bottom plot here is the sunspot number. It's a function of date for the, for the last 3.5 cycles. And on the top is the total solar irradiance. And this is compiled from 4 or 5 different spacecraft, different instruments. But it's, you have to add the 1360 watts to it. And this is the variation about that. But you can clearly see that at cycle minimum, the sun is dimmer than it is at maximum by about 1/10%. So where does that come from? It comes from, once again, magnetic fields. While sunspots are dark, the entire surface of the sun is covered in magnetic fields. So here I have an image on the left that's what you would see without a filter, showing a sunspot near the edge of the sun. The picture on the right is a magnetogram, shows the magnetic field with shades of yellow to red being positive and shades of green to blue being negative. And you can see the intense fields in the sunspot, but as you look around the sun, there's, again, magnetic fields every place. And in particular, near the limb of the sun, near the edge of the sun, wherever there's these weaker magnetic fields, you see bright stuff. They're called faculae, and they're basically caused by the magnetic field punching a hole through the surface, and you can see the bright walls on the inside. So you see it particularly near the edge of the sun. But it's these bright faculae that make the sun brighter at sunspot cycle maximum. The faculae tend to go away when the fields are much weaker at sunspot cycle minimum. So given the fact that the sun is dimmer at minimum, people look for a connection between climate and sunspot cycle. So this is a plot I made, oh gosh, 15 years ago, I guess. It was shortly after the Moberg number. And so it shows a sunspot number in black with a Maunder minimum, and then 2 different records of global, or in one case, I think it's northern hemisphere temperature. Mann et al., this is Michael Mann, is the blue line, and then Moberg is the red line. And what was noticed early on was that there seems to be a dip during the Maunder minimum in both of those temperature records. There's a dip during what's called the Dalton minimum around 1810 or so. And then there seems to be this rise as the cycles get bigger and bigger. So again, the correlation between the two seemed pretty good. However, we knew that the 0.1% change that we see in total solar radiance can't explain this much of a temperature difference. 0.1%, you put it into any climate model, and it's about 1/10 of a degree centigrade response by the Earth. So it's got to be something more than that. This led to a decade or 2 of research into what else besides total solar irradiance might influence climate. And one idea was that solar ultraviolet light, and that's shown in the series of images in the bottom left, going from cycle minimum in 96 through maximum in 2000, 2001, and back towards minimum again in 2006. And this is ultraviolet light is seen from SOHO. And you see how much brighter the sun is. It's not 0.1%, it's factors of 10 brighter at maximum than it is at minimum. So the thought was that, well, maybe that does something to our upper atmosphere that influences climate. Another possibility was cosmic rays. Turns out that when the sun is active, the magnetic field throughout the solar system is very tangled, and that keeps cosmic rays from the galaxy from getting in and hitting Earth. So when the sun's less active, like during the Maunder minimum, you would get more cosmic rays coming in. And the idea was that those cosmic rays might influence cloud formation and hence the temperature in the troposphere. Then there's this, that the sunspot cycle has been getting smaller over the last 30 years or so. So the decreasing size of recent cycles have led some of my colleagues to predict that there's going to be another grand minimum like the modern minimum. And given what appears to be a strong influence on climate, maybe global cooling. So out comes the press. And again, this is a decade ago, June of 2011. And here they ask, are we heading for a modern minimum? Will there be a little ice age? The ice age is coming, so forget maybe, it's coming, and maybe it's already here. So that was a decade ago. We haven't seen a little ice age nor a modern minimum. In the last 10 years, there's been a concerted effort within the community to look at the sunspot record. And I mentioned the fudge factor that Wolf put in, the 0.6. We really don't want to match ourselves to Wolf. So if you take out that 0.6, everything gets bigger. But it turns out another one of the keepers of the sunspot number, Max Waldmeyer, also from Zurich. Max took over the sunspot number in the 1940s and decided that he was going to change the way he counted sunspots, and he didn't really inform the rest of the community. We've really had to dig deep into his journals to recognize that he decided that when you go to count sunspots, big ones count more than little ones. So a big sunspot would count as 5 and a little one only 1. And that inflated the sunspot number since the 40s. So a fairly large group through a series of worldwide meetings have looked at the record and come up with a new sunspot number called version 2.0 with the idea that, yeah, it may change again. But the key thing for climate that comes out of that is that we now see that the big cycles in the middle of the 20th century are about the same size as those that were in the middle of the 19th century, in the middle of the 18th century. So it's not like the cycles have been getting bigger and bigger. And so when you look at that sunspot record and temperature that's shown in blue here, it now looks like the connection between solar variability and climate is more consistent with this 0.1% variation in total solar irradiance. So about 1/10 degree centigrade. So given that the sunspot cycles are getting smaller here. So here's the last, 170 years or so. And the temperature on the top is from the British Hadley Climate Research Unit. And this is a temperature, global temperature, and you see, again, the dramatic rise here over the last 50 years or so. And while that temperature's been going up, the cycle's been getting smaller. So, and it's not changing the slope of that. So, to conclude, first of all, magnetic fields, they're everywhere throughout the universe. They're the most magical things. Magnetic fields in their interaction with the hot ionized plasma on the sun produce an array of solar structures. For example, sunspots, faculae, prominences, coronal loops, coronal streamers, and that's just the short list. There's a host of others. The violent disruption of these magnetic features in solar flares and coronal mass ejections produces the space weather that can adversely affect our modern technologies. For example, satellites and power grids. When prior to us using electricity, prior to electric wires and telegraphs and so forth, most of space weather didn't impact us at all, other than producing aurora borealis, which again, pegging it to the sun didn't happen until much, much later. There were all kinds of fanciful ideas about what caused the aurora borealis. But in this modern age, space weather does affect us. It costs billions of dollars in what it does to satellites, and it could cost that or more by taking out transformers during a big event. Finally, while solar variability can impact global temperatures at the 10th of a degree sea level, this is small compared to the half a degree C increase that we've seen already. So in spite of even some of my colleagues claiming that, you know, the sun is doing all of this, no, you can't blame the sun. Finally, I'd like to invite you to look at 3 different websites. One is the one I share with Lisa Reitmeyer, a former student of mine who's now a researcher in Boulder, solarcyclescience.com. I try to update that every month. And then betacapea.com is an online encyclopedia, basically. And I have an article on there in their planetary section about the sun and climate. And then living reviews in solar physics. These are all free. You don't have to pay a fee to see them. But living reviews in solar physics, I've done 2 reviews on the sunspot cycle for them, and they have asked me to do a 3rd one sometime this year.